Hello everybody and welcome back to Tutoring Math. We are a nonprofit organization and we offer free tutoring in all subjects up to and including AP Calculus BC. You can check out more information about us in the description. Alright, before we dive into community forming arguments and combinatorial identities, I want to quickly go over the notation that's going to be used heavily in this video. And we're going to be using these binomial coefficients, which are going to denote combinations. And community forming arguments rely heavily on this idea of combination, where a combination allows us to find the number of ways that we can choose k items out of a total of n items, where order does not matter. All right. So how do we calculate a combination? Well, we first find the number of ways that we can choose the k items where order does matter. And we can do this in n times n minus 1 times n minus 2, so on until n minus k plus 1 ways. Because remember, the first object that we choose has a total of n choices to choose from. Then for the next object we have n minus 1 choices, and so on until for the kth object we have n minus k plus 1 choices. But now we want to factor in the idea that order does not matter. So we do this by accounting for the number of ways that we can rearrange these k objects. So for any k objects, we can rearrange them in k factorial ways, right? So we divide this entire expression by k factorial. Now if we simply multiply the numerator and the denominator by n minus k factorial, we get n times n minus 1, and so on until n minus k plus 1 times n minus k factorial over k factorial times n minus k factorial. But notice that on the top, we've essentially written n factorial in a different way. Because n times n minus 1 all the way up to n minus k plus 1, if we multiply that by n minus k factorial, that essentially gives us n factorial. So this expression simplifies to n factorial over k factorial times n minus k factorial. And this is essentially how we calculate a combination. Now we can proceed with the rest of the video. So in today's video, we're going to be talking about committee forming argument, which is a very powerful technique when it comes to proving combinatorial identities. So to demonstrate how a committee forming argument works, let's look at this example. So we're given that n choose r equals n choose n minus r. So if we wanted to prove it, it's fairly straightforward to do with algebra, right? Because by the definition of a combination, both the left-hand side and the right-hand side are counting n factorial over r factorial times n minus r factorial. However, let's try to do this with a different approach. Let's say we wanted to prove it using committee forming arguments. So in that case, let's say we wanted to choose a committee. We want to choose how many ways that we can form a committee of r people from a group of n people. So we have a group of n people and we want to choose r of those to form a committee within the group. Now clearly the left-hand side is choosing r people to form a group from a total of n people. Now we want to show that this is essentially the same thing that the right-hand side is counting. So notice that n choose n minus r is the same way as choosing n minus r people from the group of n people. And the reason that this is equal to choosing r people from n people is that we're choosing the people that are not on the committee. So essentially we're saying we're choosing n minus r people, and we're saying that those are not going to be on the committee, which is essentially the same thing as choosing r people who are going to be on the committee. So this is how a committee forming argument works. We're going to show that the quantity on the left side of the equation counts the same thing, but in a slightly different way than the quantity on the right side of the equation. Let's go ahead and see how this works in another example. Okay, so the first identity that we're going to be proving using a committee forming argument is Pascal's identity. And essentially it says that n choose r plus n choose r plus 1 equals n plus 1 choose r plus 1. So often when we're doing a committee forming argument, it's best to start with the side that looks simpler. And in this case, the right-hand side is only one binomial coefficient, so let's start with that. So the right-hand side is counting the number of ways that we can have an r plus 1 person committee from a total of n plus 1 people. So from an n plus 1 person group. And now we want to show that the left-hand side is also counting the number of ways that we can prove that we can form an R plus 1 person committee from n plus 1 people. So notice now that the left-hand side is actually a sum of two binomial coefficients. Usually in a committee forming argument, this means that we have to use casework. So let's break up the left-hand side into two cases. Consider a person X, who is in this group of n plus 1 people, and we want to break up the cases based on whether X is in the committee or not. So let's let case 1 be that X is on the committee. If we know that X is going to be on the committee of R plus 1 people, then we still need to choose the remaining R people to form the committee, to complete the committee. And we have n people to choose from, because X is already on the committee, so that reduces the total number of people from n plus 1 to n. So case 1 gives n choose R ways to form a committee of R plus 1 people, given a total of n plus 1 people to choose from. Now case 2 is that X is not on the committee. And if X is not on the committee, then we know that we still have to choose R plus 1 people to complete the committee, but now there's only n people to choose from because we already know that X is not on the committee. So this case gives us n choose R plus 1. And since these two cases are exclusive, meaning only one of the two can happen, not both, since X can either be on the committee or not, we can add up these two cases to give us the total number of ways to create an R plus 1 person committee from n plus 1 people. So essentially we've shown that n choose R plus n choose R plus 1 equals n plus 1 choose R plus 1. And so using committee forming argument, we have proven Pascal's identity. And let's move on to the next example. All right, here is our next combinatorial identity, and let's see how we can prove it using a committee forming argument. So on the left-hand side, notice that we have a sum of binomial coefficients, and essentially this means that we should probably use a casework argument. So let's start with a group of n people. And out of this group of n people, let's say we wanted to choose find the number of ways to choose a 0-person committee. So essentially, n choose 0 finds the number of ways that we can have a 0-person committee. But instead, let's say what if we wanted a 1-person committee? Well, then n choose 1 counts the number of ways that we can have a 1-person committee, and so on until n choose n counts the number of ways that we can have an n-person committee. So essentially, the left-hand side calculates the number of ways that we can have a committee with any number of people. So it essentially gives us the number of ways that we can have an arbitrary number of people in a committee. So we've found the number of ways that we can form any committee using the sum of binomial coefficients. And now let's find an argument that counts the same thing for the right-hand side. So on this side, notice that we can also form a committee with an arbitrary number of people, but by deciding for each group member whether they're on the committee or not. So since each group member has two choices, because remember they can either be on the committee or not, and since there are also n group members, then we have a total of 2 to the n ways to make the choices for all the group members to decide whether they're on the committee or not. So therefore, the right-hand side also counts the same number of ways to create an arbitrary committee. And so we've proven this combinatorial identity, and let's move on to the next one. All right, here is hockey stick identity, and it states that the sum from k equals p to n of k choose p equals n plus 1 choose p plus 1. So essentially this says that k choose p plus k plus 1 choose p plus k plus 2 choose p, and so on until n minus 1 choose p plus n choose p. The sum of all these binomial coefficients equals n plus 1 choose p plus 1. So let's see how we can prove this identity using the committee forming argument. So on the right hand side, notice that we have a group of n plus 1 people, and we're forming a committee of p plus 1 people. So now let's find an argument that counts the same thing for the left hand side. Well, for the left-hand side, we clearly have to use a casework argument because we have the sum of binomial coefficients. So let's say that let's say that we have n plus 1 people standing in line, in a line of some sort, and let's number them from 1 to n plus 1. So we have person 1, person 2, so on until person n plus 1. Now let's say the first case is that the largest numbered person in the committee that we're choosing is p plus 1. If that is the case, so if the largest numbered person is p plus 1, then we still need to select p people to complete the committee, because remember, our committee size is p plus 1. But now we only have p options to pick the committee members, because the largest numbered person is p plus 1, so all the other members must be less than p plus 1. So this case gives us p choose p ways to form our committee. Now let's say that the next case, let's say the largest numbered person is p plus 2. Then by a similar argument, we have p plus 1 choose p ways to form this committee. And we continue until the largest numbered person in the committee that we form is n plus 1. And if this is the case, then we have n choose p ways to form our desired committee. So essentially, if we sum over all these cases, we arrive back at our identity, and so therefore we've proven hockey stick identity using a committee forming argument. Let's move on to the last example, which is van der Maan's identity. So here is van der Maan's identity, and this identity is quite tedious to prove with algebra, but thankfully there's a really easy way to prove it using a committee forming argument. So let's go ahead and see how we can prove it using committee forming. So this identity, if we expand it out a little bit, we have m choose 0 times n choose r plus m choose 1 times n choose r minus 1, and so on until m choose r times n choose 0. And this identity tells us that this whole expression on the left is equal to m plus n choose r. So now how do we prove this using a committee forming argument? Well, we're going to start with the right hand side because it is just one binomial coefficient compared to this sum of binomial coefficients on the left. So the right hand side, let's come up with a scenario that there's a club of m plus n people. And just to make this easier to visualize, let's say there are m males in the club and n females. And from this club of m plus n people, we want to choose r to form the committee. So we're going to have an r-person committee that we're going to choose from this total group of n plus n people. Now we want to count this same way. Now we want to count the number of ways to choose an r-person committee from a group of n plus n people, but we want to show that the left-hand side also counts the same thing. So the left-hand side, since it's a sum of products of binomial coefficients, we can do casework on this left-hand side. And so the way we're going to do casework on this is we're going to divide the cases based on the number of men. The number of men in the committee that we're choosing. So if there are k men in the committee of r people, then there have to be r minus k women, right? Because there's a total of r people in the committee. If k of them are men, r minus k must be women. So now there are going to be m choose k ways to pick the men from the total of m men that we have in our club. And there's also going to be n choose r minus k ways to pick the woman from our club, because remember our club has m males and n females. So from the total of m men, we're choosing k, and from the total of n females, we're choosing r minus k. So now if we sum this case over all possible values of k, then we essentially create our identity, which is van der Maan's identity. So you can clearly see how powerful committee forming arguments are in terms of proving combinatorial identities. And that was it for this video. I hope you guys found it useful. If you have any requests or suggestions, you can use the form in the description. And thank you for watching.